We'll see how late I've already been able with this and how far we can move. The first thing that I want to discuss fluctuations, and I want to discuss fluctuations in a super simple case when there is no noise and no change. A few comments before we start. So first of all, I'm talking about fluctuations in finite time, right? I'm not trying to see the long time deviation for the limit, which is a much more complicated topic. Now, fluctuations in finite time are something that has been relatively well known, at least when the interaction kernel is existing. The main paper was probably the one by Hernandez and Aléa, but then there's a very simple way to see that in the deterministic case. And then here I'm actually pulling a recent preprint by one of my former students. So it's Wong, Zhu and Zhu, and they treat the stochastic case, which requires quite a bit of stochastic machinery. But you can take their proof, apply it in that case, and then it's like very, very simple. And this is what I want to show you. Let me recall, right, that I have defined this empirical measure, which is a random measure. It's also a random measure if I don't put any diffusion because my initial conditions are random. Right? It's just simply then propagated by. And we have, in that case, we know that this empirical measure is an actual solution to the initial equation. So, well, if we have these two, right, there's a very forward way of thinking about fluctuations, which is to say fluctuations are the difference between the two objects, and since they both satisfy nonlinear PDE, we can write down exactly what is the equation on the difference, and we can try to pass to the limit in this equation. I'm going to define the fluctuation, which is eta n, right, which is the proper rescaling. And I can write an equation on n. That's very, very easy. And you see that I have here quadratic terms, so you need to decide how you want to split them, right? It's a very nice equation. And we would like to pass the limit into this equation, which then mu n should converge to a bar. And so we should have a linear equation of the fluctuation that is, of course, the linearized to the. There's one thing that you have to pay attention to at this point, however. One thing. There is a strong temptation to study bounds on eta n from the equation and to try to propagate them. And this would be a horribleness. Not that this doesn't propagate anything. For example, assuming that f bar is smooth, this very easily will keep the bound on the L1 norm of the time. So I can, that's because, oh yeah, I should say this, I'm still within the but yesterday was the dimension on my P. Sure. Remind you. So, right, the case divergence free, so this doesn't play any role, right? And then I play with the gradient of that bar, so if that bar is C1, you know, then it's all good. And then I have d over dt of eta n in L1, right? First of all, then something like k in infinity, that bar shifts, right? And so once you see this sort of bounds, there is a huge temptation to think that you're going to be able to use them. Right? You're just not. So the problem here, right? So eta n is a measure, so I should replace L1 by total variation, right? And the total variation norm of eta n from its definition is extremely easy to calculate, right? Because this is the sum of direct mass and this is a continuous object. So the sign absolute doesn't matter, right? So this is 2 square root of n, which of course has a very, very poor idea of going to infinity. And you won't have any strong norms on that, right? At all. Now, this brings me to I should make a further comment on the last estimate that I showed yesterday, because I wrote it correctly, but one has to be a little bit careful. What I actually showed you from the entropy inequality is that for all phi in L infinity, I could bound the integral of phi against that. And so I'm going to write this in a relatively careful manner. What we prove, and in particular, I really want to emphasize the order, because if I had swapped the order, then this would be the expectation of an L1 norm of eta n, and then we should be a little bit worried about the entropy result. But here, you choose phi first, so phi is a deterministic object, and then you take the expectation. So this is really not an L1 norm. And again, if you want to control that, right, you can try to write down the Fourier coefficient of eta, and that tells you that every Fourier coefficient is bounded, because I can take as phi exponential ikx. And so what I get here out of this bound is a distribution whose decomposition in Fourier is in L infinity in Fourier. And that's an object that at best is in H minus alpha larger than the other two. And another way of seeing that, which will confirm the scale, is that eta n scales like a white noise. And more specifically, like the Gaussian noise, which it is at the origin in essence. Because if I take the xi0 to the iid, you see that this ultimate sphere minus phi bar is the average with respect to. And so this is something that converges to a Gaussian. Centered at 0, of course, and with a variance that you can also easily calculate this, right? And the variance is the integral of phi square at 0 minus phi at 0 for every phi. So it's not a white noise, right? Because you have f here. So it's not spatially homogeneous, but it obviously scales like something like this. So, and this is another important comment, even though I will do essentially a deterministic proof here, so I will do a normal Shor argument for every instance, right? The only way that I can correctly appreciate this is by really understanding eta and the limit as the random measure, the random distribution, sorry. So if we really wanted to do something like this, right, we would have to try to propagate negative subleved bounds on an equation like that. And if you know a tiny bit about transport equations, you know that if that field is not smooth, propagating negative subleved bounds on a linear transport equation is in general not possible. So we would really have a hard time with K unbounded, for example. We would really have a hard time trying to prove a bound like this on the solution to this. And just take limits, because I have a bound. Weak star convergence, some of this things, right? So we can restart the same. But it's weak star in probability space, right? And I just extract the subsequence. Now I want to take the limit. The limit here is obvious, and the limit there is obvious, because FR is smooth. The limit here seems to be a bit more of a problem. because this doesn't have a lot of regularity. Basically, it's an object that is in now infinity, and that's it, right? And I'm trying to multiply it to get something that is in h minus alpha, and that looks extremely scary. And it again looks at the level of the equation like something that I'm not going to be able to do trivially, because I'm saved again by the large deviations. I'm going to put f bar, right? And then this guy, there's no problem passing to the limit because f bar is smooth. And then I have the commutator here. That is actually quadratic in the difference mu n minus f bar. And we know that Cn goes to 0, like 1 over square root of n. Because Cn, once I'm going to integrate it against the test function, has again exactly the form that I had in my large division result. Let's take the test function. Let's look at Cn. Well, I'm going to, write explicitly. And this is. So again, this is going to be a weak convergence. Following the same type of remark that I've made here, right? Again, phi is deterministic, so we take the expectation first. It's a really fun argument because if you take it from the right angle, it becomes entirely true. Now, again, if you have diffusion, right, this is a lot more painful because you have additional stochastic terms here. You need to rescale them, and you need to explain what the limit is. And the limit of this term is not going to be something nice for the same reason that none of the limit of any stochastic object here has been very smooth. Right? And then you have to work more than what I'm prepared to do in this model. But so that's where you have a real figure, right? Something that but the proof in the deterministic case, you get the limiting equation. This limiting equation, by the way, is well put, and that's easy for short time. And that's easy because now f bar is smooth and f bar is everywhere. So now I don't have any question of having the transform equation with non-smooth drift. Drift is smooth. Well, I can also get you that's this distribution makes sense what you want, right? Already you have no derivative of that format. Well, so in particular, that means that I don't actually need to extract the subsequence because all subsequences converge. And we know the initial data. And so it shows to you that at the level of the empirical measure, right, the fluctuations are indeed of order 1 over square root of n. And we can calculate them easily. And if you try to push this for long times, everything goes up to your face. Argument, okay. And I mean everything because we estimate grow exponentially over time. The commutator estimate grows exponentially over time. Because the entropy, the relative entropy grows exponentially.
But you have a raised convergence, so maybe a log n.
By log n, you're okay. Initial log n, you're always okay, right? But that's usually very bad. However, if you had propagation of fields uniform in time, then all those estimates will be uniform in time. And now it will be the limit uniform in time as well. No question. Let's go to the next. So we've done the initial limit for bounded objects. Now, tweaks for first order on the torus, let's completely finish that. So let's prove that there's always an infinite. And I don't want it to degenerate. Scales with n as long as it does not degenerate, it's still good, but all right. So here we come to a further question, right? Going into statistical methods. So we have this control on the joint flow, and that's what's giving us a control on the knot. And now you can ask, well, would be really nice to actually be able to have balance on the marginal. And here's the problem. Okay? There's a relatively obvious problem. We can write the PDE that is satisfied by the marginal. You're going to move the first k particle, and now there's a question. So you pick an I between 1 and k, right? And that's the particle xi that you're following. The question is it interacting with another? Are you looking at its interaction with another of the first k, or are you looking at its interaction with one of the remaining particles? If it's another of the first k, then it's all good and explicit, and we have the following term. If you're interacting with one of the other n minus k, then you cannot represent the term with a marginal of k. Because now you need to know the position not of k particle, but of k plus 1. And all the contributions are the same because by symmetry they are identical, and you end up with a term like that. So you have a very well-known phenomenon, right? That to calculate the marginal of over k, you need to know the marginal of over k plus 1. So you can essentially never stop, right? What you have is the well-known GKY hierarchy. And this really blocked most of all reasonable efforts to try to get balanced direction in the model. And the first attempt, right? Puglianti had a result at the end of his teach, for example, if I remember correctly, where just to say, well, let's treat this as a source term for this equation. But then any norm that you're propagating on f and k requires the norm of the gradient of f and k plus 1. And so you're losing a gradient at every step, right? So which essentially puts you in an analytical space for f and for k if you want to get any result. Recently, but much more recently, people have been able to sort of handle the hierarchy for k Lipschitz. And there's a result by Goltz and Inicia, Jens also have done something a little bit, right? In that regard, control on F1, and for this would be for any F k. Again, with k Lipschitz, but it doesn't directly use the hierarchy as is because it would face the same problem. It seems that we're sort of stuck. And yet there is a trivial solution here, at least if you're in a confined domain. So I'm going to take the choice. I'm again going to take divergence of k, which is equal to 0. You actually only need to control the negative chance of divergence. So repulsive gradient will be okay. And the solution is very obvious, very trivial. The diffusion. Just use the diffusion. Use the diffusion to avoid losing a derivative. This is the heat kernel with regularizers. And in a sense, it's very funny that you can have any result using this stupid ID until very, very recently. And then about a year ago, there was a paper by Dan Lacker. I'm not sure if it's published yet. And he's using the entropy, and he's using this. And then what he can do is he can get explicit control on the relative entropy for each marginal directly. And this gives you a convergence of the marginal. You notice that this term is of order 1 over n, right? And here the correction to 1 is also of order 1 over n. And so it turns out that the marginals are converging to the limit at order 1 over n. And not 1 over square root of n. Now, some people are surprised by this, others are not, so I'll let you choose. The point here is that there are more cancellations in the marginal than there are in the empirical measure. The empirical measure, again, we just proved that it could not converge at better than 1/1 root of it. This is not. And at the same time that Lacker proved this out, right, we were working on the case of non-exchangeable systems. And we actually needed something like this as well. And so it was really, because it happened basically within a few months of each other. But we are using LP bounds on the marginal. And the use of LP bounds on the marginal then here will completely break the limit k bounded and will let you handle any LP, any k that is an LP. I'm going to show you the calculations. They are again very easy. So it's good for Friday morning. And the conclusion is very simple and very powerful. Let's do this. Time there is fast. And so this has zero contribution because k is divergence free. This I can integrate by part. Okay, so I play with a gradient, but I have a control of the gradient. I'm just going to do a Holder estimate. So it's I wrote it -1, yes. Now to do the Holder estimate, you need that t is larger than 2. And then I'm going to, take first an L2 of this one with the right weight, and I will have an Fk to some power that will remain, and then I will take another Holder estimate. But once you see the scaling, there's only one possible answer here, and it's that this is less or equal than, for example, and it could have a product. I'm just bounding the product of the verified, the VRC exponent by this. Okay. And so very naturally, what comes out of those Holder estimates is an LP norm of whatever was here. Which is what it should. And even though this looks bad, it's good. Because you have another very simple regularizing effect here. Which is that I can do another Holder by taking the P norm here and then the star norm. And k, I only need to integrate it with respect to one variable. This is less, right? That's less than general. K. Next one is 4. F P plus 1P. Okay. I don't care that there's an X here, so it's absolutely no role regarding X translation. So what do I do out of all of this? All right, that I'm just going to put a small number in front of it and eat it by that. Okay? This guy right therefore will have a constant that depends on P and on sigma. That's fine. And I'll have the norm itself. Right, that's fine. And I have a sum here, right? I have a sum of k terms. So I have k times that. And the other one looks exactly the same. It's k, and I get kn minus here, and well, for the last, this is estimate also on the last equation. And then I have the norm of k sum. LP norm. So it's still a hierarchy of ODE, but it's a hierarchy of ODE now. That works. So I'm not going to give you the full calculation. It's not very hard. It's just simple, right? You just start from F1, for example, then you integrate all the time, right? So you'll get factorial out of the n interval times that you're going to take. And the factorial will exactly help compensate the factorial that you get. Let me show you why at least this is the right scale. Okay. So let's say that I have a that is something just like this. Okay. Because initially you might be scared of the k factor. Let's say that xk we hold this is comparable. Okay. So that means you that xk is of course that's a 0, right? Exponential ck. And you might be very, very scared of the exponential ckt. You shouldn't. This is what it's supposed to be. Remember that fk initially, for example, if the particles are iid, it's the product of k terms. This has exactly the same scaling in class. xk0, if we believe that, right? This is like f0 to the power power k. So you get exactly the same estimate at later time than what you had at time 0, except you grew a little bit the norm, which is a big surprise. So this kind of old scary looping OD are actually completely natural in that scale.
While you're erasing, is it clear where we use the layer on the torus and not on the whole space?
Yeah, I'm going to come.
Okay.
So first, I want to tell you what the conclusion is. The conclusion you have here is that these things are preserved for a time of order 1. And then after a time of order 1, if you do it like that, the estimate goes up. And it blows up because I said, yeah, you have k interval in times, and that gives you 1 over factorial k, and that compensates with the 1 by that factorial that you use here, yes. And then you get a tk, right? And there is nothing to compensate for the tk. So you need tk to be less than something, right? So the constant that show up. Otherwise, you have plus infinity. So this shows that there exists a constant, right? There exists a time, r, such as that's the basic result. And now I have 5 minutes to make a lot of points. There's a lot to say. The proof is extremely simple, but there's a lot to say. So first of all, this is not directly a proof of propagation of fields. And it's actually better than that, because at no point in that proof do I need to assume that I'm infinitely closed. As long as you give me a bound like that on the LP norm or the marginal, and it's not so surprising that I have a limit. If you want to remove that, you can. Now you need k's. Because the same proof that I had done here, right? I can do it not on f and k, but on f and k minus f bar s rise k time. I do that, I have a few extra terms because f bar s rise k times does not solve the right hierarchy. So if you want to do the proof, simply you need k in L2 instead of better than L1. But if k is in L2, then I can do an L2 proof of that on the difference and it works the same. And except now, instead of having this, I have that times an epsilon. And then my time here behaves like 1 over epsilon. So this does give you propagation of chaos if you want it, and it then does give you propagation of chaos for any finite time. And it gives you the rate of convergence in 1 over n. This doesn't work if I take k, k here could scale with n, it doesn't need to be fixed. And this argument doesn't work for k in L1. If k is in L1, you could probably still make it work, but for k that scales with only the L1 norm that is bounded, right? So k converges to a measure, this won't work. which is sort of reassuring because K scaling with N and L1 is the Boltzmann scaling interaction. Or would contain the Boltzmann scaling interaction. This will not tell you anything. Where do I need the torques? Well, I don't, but I need this to be to be true. Or basically any of the applications that I mentioned, if you're not in a bounded domain. K will be locally in an LP. Might have some decay at infinity, but they won't fit. So you will not be able to bound this. So it's not that the result doesn't work in unbounded domain, it's that the assumptions that you would need to make this proof work as is in an unbounded domain is not good. What can we do for second order system? Well, we can actually extend the proof for second order system, but now it becomes a little bit tricky. This can be used to derive a Blasov-Poisson-Fokker fault in the repulsive case. But I need to change the quantities. And for second order system, what I need to put here is I need to put the weight that depends on the reduced energy. I need moments in velocity. Because what I just said about this not being physical if the domain is not confined, right? For second order system, it depends on x. So it is not going to be in any of these spaces.
When you think of the unbounded domain, do you think of a confining potential, or are you thinking of unconfined?
The second order or first?
Yes and yes. Whichever order you prefer. Go for it.
Okay, so second order, the confining potential will not be the big problem. So you could extend the domain in X. That's relatively easy. The problem is then there's no way that you can get confinement for trajectories. Yeah, and you need to use them correctly. So that's what I'm saying is that in the second order case, what you're putting here is you're putting an exponential of something which is like the sum over I of EI squared. But I don't propagate only the kinetic energy, so I need to add the potential energy as well. The potential energy reduced to the K particles that I'm. You have diffusion, so you don't propagate Gaussian bound with a peak variance, so you need here something that you can propagate in second order system, provided that the potential phi has a sign. That's of course also for longer interaction, but not for gravitation. Now, if you want to unbound the space, can you give me a confining potential or nothing? I can still do it because I will just add moments in X and whose will fit with the system.
If you have a confining potential, this won't be a problem, really, right? This interaction current.
Yes, it still is. You have to be careful. Because this still blows up, so you still need to add a weight in here so that the corresponding interval will be finite. Or you need to explain to me that you know for sure that all single trajectories are confined. And so first order outside of the bounded domain is actually harder, I think, in general, because now you will need to make sure that where you put the confining potential or not, I'll have to put these moments in the exponential Gaussian moment X. And then how is this going to react with the false term? Second order, it's very, very simple because the way you put the confining potential, right? But first order, now you will have it, when I'm doing this, right? I will have a term which is the derivative of that in X hitting against that. And that in general, I don't know how to do. Nice, your confining potential leads to a nice energy. But
Okay, any questions?
A quick question about the speed of convergence. So I would expect maybe something like 1 over n to the k over 2 has to be a 1 over n.
has to be 1 over n because you have terms of order 1 over n there. If you were capable of showing the faster speed of convergence with this type of strong norms, you would get contradiction.
Okay, so it doesn't improve with the number of marginals that.
Every finite marginal converges at order 1 over n. There's a constant in front of it which actually goes up as you increase k. Because the joint law Fn cannot converge.
Okay.
The joint law Fn measures the fluctuations of the empirical measure. And so it cannot converge better than 1 over square root. But you have a fun entropy picture here. If you look at Dan's result, right? Because essentially, if I prepare well, so you start with the entropy of the joint law and the entropy of the marginals that are all at 0. Then you have an initial time layer, right? The entropy of the joint law will jump immediately to 1 over square root of it. And the entropy of the marginal will jump only to 1 over n. So you have a gap of entropy between the joint law and the first marginal, which looks like there is some sort of irreversibility that is going on after rescaling. Anything there. That's good, but it does suggest that you see a little bit, right? That's what you see in Boltzmann, right? Because in Boltzmann, if I'm looking at the entropy of the joint law, it's constant. Yet the entropy of the one particle distribution, it decreases, right? If you start with chaos, the two are coincide at the origin, and then one is constant and the other one goes down. There is any way to exploit this using that framework?
Thank Pierre Emmanuel again. We have a coffee break.